When a massive star dies in a supernova, it can leave behind one of the most extreme objects in the universe, a magnetar, a neutron star with a magnetic field trillions of times stronger than Earth's, so powerful it could warp atoms into thin, needle-like shapes. Every magnetar we've ever found appears to trace back to the explosion that created it. You can follow its motion backward through space like rewinding a bullet's path to find the gun. But in 2008, astronomers discovered a magnetar that broke this pattern. When they measured its motion and traced its trajectory backward through time, it didn't point to the supernova remnant everyone assumed had birthed it. It didn't point to any obvious explosion at all. So the question became, where did this thing come from? And the possible answers are extraordinary. Before we dive into this mystery, if you find these kinds of deep explorations of the universe interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you've experienced your whole life, but probably haven't thought too deeply about. Magnetism. You felt it every time you stuck something to your refrigerator door, every time a compass needle swung toward north, every time you held two magnets close together and felt that invisible push or pull between them, that strange force reaching across empty space without anything visible connecting them. Magnetism is one of the fundamental forces of nature, and it exists on a spectrum that stretches from the incredibly weak to the almost unimaginably powerful. The Earth itself is a giant magnet. Deep inside our planet, a churning ocean of liquid iron generates a magnetic field that extends thousands of kilometers out into space. This field is what makes compasses work. It's what deflects charged particles streaming from the sun and protects our atmosphere from being slowly stripped away into the void. Without Earth's magnetic field, life as we know it probably couldn't exist here. And yet, by cosmic standards, Earth's magnetic field is extraordinarily weak. At the surface, it measures about half a Gauss. A Gauss is a unit scientists use to measure magnetic field strength. Half a Gauss. That's what stands between us and the full fury of the solar wind. It doesn't sound like much, and compared to what we're about to discuss tonight, it really isn't. A typical refrigerator magnet generates a field of about 50 to 100 Gauss. That's roughly 100 to 200 times stronger than the Earth's entire planetary magnetic field. And it's barely strong enough to hold up a sheet of paper against the pull of gravity. The powerful magnets used in MRI machines, those large tubes that take detailed images of the human body, generate fields of around 15,000 to 70,000 Gauss. These are strong enough that unsecured metal objects in the room can become dangerous projectiles. You have to remove watches, belt buckles, anything ferromagnetic before going anywhere near one. At these field strengths, magnetism demands genuine respect. But even the strongest MRI magnet on Earth is absolutely nothing compared to what exists in certain corners of the universe. To understand what a magnetar truly is, and why the one at the center of tonight's story is so strange, we first need to understand where magnetars come from. And that means we need to talk about how stars die. Stars spend most of their lives doing one essential thing: fusing hydrogen into helium deep in their cores. This process releases an enormous amount of energy, and that energy does two critical things simultaneously. It makes the star shine, producing all the light and heat that sustains life on planets like ours, and it creates an outward pressure called radiation pressure that pushes against the relentless inward pull of the star's own gravity. For most of a star's life, these two forces exist in near-perfect balance. Gravity pulls inward, radiation pressure pushes outward. The star holds its shape. It neither collapses nor flies apart. It just sits there in space, burning steadily, converting hydrogen into helium for billions of years. But this balance can't last forever. Eventually the star runs out of hydrogen fuel in its core. What happens next depends entirely on how massive the star is. A star like our Sun, a relatively modest star by cosmic standards, will swell into a red giant, shed its outer layers gently into space, and leave behind a small, dense object called a white dwarf. A white dwarf is roughly the size of Earth, but contains about half the mass of the Sun. It's dense, certainly, but it's not extreme by the standards of what the universe is capable of producing. It slowly cools over trillions of years, fading from white to yellow to red, and eventually going completely dark. But stars much more massive than the Sun face a far more dramatic end. Stars 8 or more times heavier than our Sun burn through their fuel much faster than smaller stars do. Where the Sun will shine for about 10 billion years total, a star 20 times more massive might exhaust its hydrogen in just a few million years. And when the hydrogen runs out in one of these massive stars, the star doesn't quietly fade. It begins fusing heavier and heavier elements in its core, one after another, in a desperate attempt to keep generating energy and holding itself up against gravity. Hydrogen becomes helium, helium becomes carbon, carbon becomes neon, neon becomes oxygen, oxygen becomes silicon, and silicon finally becomes iron. Iron is the end of the line. This is where the physics changes completely. Every fusion reaction before iron released energy, and that released energy is what kept the star's core hot and maintained the outward pressure that held the star up for millions of years. But fusing iron doesn't release energy. It actually absorbs it. So when the core of a massive star finishes converting its silicon into iron, the energy source that has supported the star for its entire life simply switches off. In a fraction of a second, the core loses its battle against gravity. And what happens next is one of the most violent events in the known universe. The iron core, which at this point might be roughly the mass of our Sun, compressed into a volume about the size of Earth, collapses under its own weight. The collapse is catastrophic. It happens at roughly a quarter of the speed of light. In less than a single second, the core goes from being thousands of kilometers across to being about 20 kilometers across. 20 kilometers. About the width of a modest city. The matter is compressed to densities that defy any ordinary description. The protons and electrons in the iron atoms are squeezed together so forcefully that they merge into neutrons. The entire core becomes a ball of neutrons packed so tightly together that a single teaspoon of this material would weigh billions of tons on Earth. More than every building in a major city combined. More than every ship ever launched by humanity. This sudden collapse sends a shockwave outward through the rest of the star. The outer layers, which are still falling inward when the core reaches its maximum density and suddenly rebounds, slam into this shockwave and are blasted outward into space in a colossal explosion. This is a supernova. For a brief period, just a few weeks, a supernova can outshine an entire galaxy, billions upon billions of stars, and a single dying star temporarily burns brighter than all of them combined. The explosion flings the star's outer layers across light years of space at speeds of tens of thousands of kilometers per second, creating an expanding shell of hot gas and debris called a supernova remnant. These remnants glow for thousands of years as they slowly expand, cool, and mix with the surrounding interstellar gas, enriching it with heavy elements that will eventually be incorporated into future generations of stars and planets. But the real story, the thing that matters most for what we're discussing tonight, is what gets left behind at the center. The collapsed core. A neutron star. A neutron star is one of the most extreme objects in the known universe. It's roughly 20 kilometers across, about the size of a large city, yet it contains between 1.5 and 2 times the mass of our entire sun. All of that material compressed into a sphere smaller than many countries on Earth. The surface gravity is about 200 billion times stronger than what you feel, standing on solid ground right now. If you could somehow stand on the surface of a neutron star, which you absolutely cannot because the gravity would flatten you into a thin film of atoms in less than a microsecond, a 1 meter fall would end with you hitting the surface at roughly 7 million kilometers per hour. Neutron stars also rotate incredibly fast. This happens because of conservation of angular momentum, the same principle that makes a figure skater spin faster when they pull their arms in close to their body. The original star might have been rotating slowly, completing one full turn every few weeks. But when it collapses from something millions of kilometers across to something only 20 kilometers across, all that rotational energy gets concentrated into a vastly smaller object. The result is a neutron star spinning at extraordinary rates, sometimes hundreds of times per second. The surface of such a rapidly spinning neutron star can be moving at a significant fraction of the speed of light. And as it spins, its magnetic field, also compressed and amplified from the original star's much weaker field, sweeps around like the beam of a lighthouse. If those sweeping beams of radio waves or X-rays happen to cross Earth's line of sight, we detect regular pulses of radiation. We call these objects pulsars, and pulsars are extraordinary. Some pulse so regularly that they rival atomic clocks in their timekeeping precision. But a pulsar, as extreme as it sounds, is actually the mild version of what a collapsed stellar core can become. Because some neutron stars are born with magnetic fields so monstrously powerful that they dwarf anything else in the known universe. These are magnetars. And understanding what separates a magnetar from an ordinary neutron star is essential to understanding why the object at the center of tonight's story is so deeply puzzling. A typical neutron star has a magnetic field of about 1 trillion Gauss. That's already a staggering number. Earth's magnetic field, remember, is about half a Gauss. So a neutron star's field is roughly 2 trillion times stronger than Earth's. But a magnetar takes this to an entirely different level. A magnetar's magnetic field typically ranges from about 100 trillion to 1 quadrillion Gauss, and sometimes even beyond that. That's roughly 1,000 times stronger than an ordinary neutron star, which itself is already millions of times stronger than any magnet ever built on Earth. To grasp how large 1 quadrillion is, consider this. If you started counting one number per second right now, without sleeping, without stopping, it would take you roughly 32 million years to reach 1 quadrillion. That's over 100 times the age of humanity. At these field strengths, magnetism stops being just a force you have to be careful around. It becomes something that fundamentally alters the behavior of matter itself. In the magnetic field of a magnetar, atoms cannot maintain their normal round shapes. The electrons that ordinarily orbit a nucleus in roughly spherical clouds are forced into tight spirals, aligned with the magnetic field lines. The atom gets squeezed into a long, thin, needle-like shape, stretched in the direction of the field. Chemistry as we know it ceases to function. The bonds between atoms, the interactions that allow molecules to form, the structures that give solid matter its familiar properties, all of it is rearranged, distorted, or destroyed by the overwhelming magnetic force. A magnetar's field is so intense that it could erase the magnetic strip on a credit card from a distance of roughly 100,000 kilometers. That's about a quarter of the distance from Earth to the Moon. Think about what that means. An object 20 kilometers wide generating a field so powerful that it reaches out across 100,000 kilometers of empty space and disrupts a tiny strip of magnetic material on a plastic card. Nothing else in the known universe generates magnetic fields this strong. Nothing even comes close. The total energy stored in a magnetar's magnetic field is staggering, roughly equivalent to the sun's entire energy output, sustained continuously over the course of 1,000,000 years. All of that energy locked in the invisible magnetic architecture surrounding an object smaller than most cities. Not every neutron star becomes a magnetar. In fact, most don't. Of the roughly 3,000 neutron stars that astronomers have identified, only about 30 are confirmed magnetars. That's less than 1%. The conditions required seem to be remarkably specific, involving just the right combination of mass, rotation speed, and internal dynamics during the first few seconds of the neutron star's existence. When you have only 30 examples of something, each new discovery becomes enormously valuable. A single exception can reshape an entire theory. The idea that such objects could exist was first proposed in 1992 by two astrophysicists named Robert Duncan and Christopher Thompson. They suggested that under certain conditions during the violent birth of a neutron star, a powerful dynamo mechanism could amplify the magnetic field to these extraordinary strengths. The key ingredient is convection. In the first few seconds after a neutron star forms from the collapsing core of a dying star, the interior is unbelievably hot, reaching temperatures of hundreds of billions of degrees. At these temperatures, the ultra-dense neutron-rich fluid churns violently, creating convective motions similar in principle to water boiling in a pot, except happening in material denser than an atomic nucleus and at temperatures beyond anything we can replicate on Earth. If the neutron star is also rotating rapidly during this brief window, only the first 10 to 20 seconds of its life, the combination of convection and fast rotation can drive a dynamo effect. This is the same basic mechanism that generates Earth's magnetic field, just operating in conditions billions of times more extreme. The result is a magnetic field amplified to 100 trillion Gauss or more. Duncan and Thompson predicted that these magnetars would announce themselves in a distinctive way. As the enormous magnetic field evolved over time, stresses would build up in the neutron star's rigid crust. Eventually, the crust would crack or shift under the magnetic pressure, releasing tremendous amounts of energy in sudden bursts of X-rays and gamma rays. These bursts would be brief, lasting fractions of a second to a few seconds at most, but incredibly intense. The remarkable thing is that astronomers had already been observing exactly these kinds of bursts for over a decade before Duncan and Thompson's theory gave them a name and an explanation. The story of those observations begins on March 5th, 1979, with one of the most dramatic events ever detected in high-energy astrophysics. On that date, a wave of gamma rays swept through the inner solar system. It was so powerful that it overwhelmed the detectors on multiple spacecraft simultaneously. The radiation was registered by at least 9 separate satellites, including the Venera 11 and Venera 12 probes, already past Venus and in solar orbit, and several military surveillance satellites orbiting Earth. Instruments that had never before been saturated suddenly maxed out their readings. For a brief moment, the intense wave of gamma rays actually ionized part of Earth's upper atmosphere, temporarily altering the electrical properties of the night side ionosphere from a source that was later determined to be roughly 160,000 light-years away. Not in our galaxy at all. In the Large Magellanic Cloud, a small satellite galaxy that orbits the Milky Way. Think about what that means for a moment. An event in another galaxy, 160,000 light-years from Earth, released enough energy to measurably affect our planet's atmosphere. The source was eventually traced to an object near a supernova remnant in the Large Magellanic Cloud and was designated SGR 0526-66. This event, now known as the March 5th event, defined an entirely new class of astronomical objects, soft gamma repeaters, or SGRs for short. The soft in soft gamma repeater refers to the fact that most of their bursts are concentrated in the lower energy, or softer, part of the gamma ray spectrum, and repeater means they burst more than once. Unlike a supernova, which is a single cataclysmic event, a soft gamma repeater fires off bursts repeatedly. It can go quiet for months or even years, then suddenly produce dozens of bursts in rapid succession. In the years that followed, astronomers discovered more of these objects scattered across the sky. SGR 1806-20 was identified in 1986 and went on to become one of the most extensively studied examples. SGR 1900+14 drew widespread attention in 1998 when it produced a giant flare powerful enough to affect instruments across the solar system. Each new discovery reinforced the same pattern. These objects appeared to be neutron stars. They were located near or within supernova remnants, and they produced repeated bursts of soft gamma rays and X-rays consistent with the cracking and shifting of a highly magnetized neutron star crust, exactly as Duncan and Thompson had predicted. The association between soft gamma repeaters and supernova remnants seemed rock solid. It made perfect physical sense. A massive star explodes, creating a supernova remnant. The collapsed core left behind becomes a neutron star with an extreme magnetic field. The magnetar's proximity to the remnant confirms its origin. If you found an SGR, you looked for a remnant nearby. And if you found both in the same region of the sky, the connection seemed obvious. The magnetar was born in the explosion that created the remnant. By the early 2000s, the picture had also expanded to include a related class called anomalous X-ray pulsars. These were neutron stars that emitted X-rays but weren't powered by the usual mechanisms. They weren't accreting matter from a companion star. They weren't spinning down fast enough for their rotational energy to explain the emission. The most compelling explanation was that they were powered by the slow decay of an enormously strong magnetic field. In other words, they were magnetars too, just observed at a different stage their evolution. Together, soft gamma repeaters and anomalous X-ray pulsars formed the growing family of known magnetars, and every member of that family seemed to fit the same origin story. Massive star, supernova, neutron star with an extreme magnetic field. This was the state of understanding on August 22nd, 2008, when NASA's Swift satellite detected something new. The satellite's Burst Alert Telescope, an instrument designed to catch sudden flashes of high-energy radiation from across the sky and alert astronomers within seconds, picked up a burst of soft gamma rays coming from a direction in the constellation Camelia Pardalis. This is the Giraffe, a large but faint constellation that sprawls across the northern sky near the celestial pole, largely devoid of bright naked-eye stars and easy to overlook when stargazing. Over the next several hours and days, more bursts followed from the same location. The source was clearly a soft gamma repeater, firing off repeated pulses of radiation in the characteristic pattern that astronomers had spent decades learning to recognize. It was given the designation SGR 0501 plus 4516, with the numbers encoding its position on the celestial coordinate grid. The discovery was welcomed, but not entirely unexpected. By 2008, astronomers had catalogued roughly 24 confirmed or strongly suspected magnetars, and adding another to the growing list was a valuable but increasingly familiar event. What made this particular magnetar genuinely interesting was not the bursts themselves, it was something else entirely: its position on the sky. When astronomers plotted the coordinates of SGR 0501 plus 4516 against maps of known structures in that region of the sky, they noticed something that immediately caught their attention. The magnetar sat remarkably close, in apparent projection on the sky, to a well-known supernova remnant called HB9. HB9 is one of the largest supernova remnants visible in the northern sky, an expanding shell of hot gas roughly 100 light-years across, the debris left behind by a star that exploded thousands of years ago. Estimates of its age varied depending on the method used, but most studies placed it somewhere between 4,000 and 7,000 years old, though some estimates stretched older. This apparent proximity triggered an immediate and natural chain of reasoning. Every magnetar that astronomers had confidently linked to a birthplace up to that point was associated with a supernova remnant. Here was a new magnetar, and right beside it, in the same patch of sky, was a supernova remnant of roughly the right age. The conclusion seemed almost inescapable. SGR 0501 plus 4516 must have been born in the supernova explosion that created HB9. The magnetar and the remnant were parent and offspring. The case looked simple. It looked clean. It looked like every other magnetar origin story astronomers had ever encountered. Several early papers noted the association, and the community largely moved on. But there's a fundamental difference between two objects appearing close together on the sky and two objects actually being physically related. The sky, as we observe it from Earth, is two-dimensional. We see objects projected onto the celestial sphere, and two things can look like neighbors even if they have no real connection in three-dimensional space. Hold your thumb up at arm's length and close one eye. Your thumb might appear to overlap with a building across the street, but obviously your thumb and the building have nothing to do with each other. They just happen to lie along the same line of sight. The same kind of coincidence happens in astronomy constantly. Stars that appear side by side in a constellation might be separated by hundreds or even thousands of light years in real three-dimensional space. A galaxy that appears right next to a bright star in a photograph might be 1 billion light years behind it. For SGR 0501 plus 4516 and HB9, the assumed association wasn't based solely on appearance. It was also supported by rough estimates of distance and age, but those estimates carried significant uncertainties. The distance to HB9 was not precisely known. Different techniques gave different values. The age estimate spanned a wide range, and the distance to the magnetar itself was even less certain, because measuring the distance to a faint, compact object, something only 20 kilometers wide and thousands of light years away, sitting in a complicated region of the sky full of diffuse gas and overlapping sources, is one of the hardest measurements in all of observational astronomy. These uncertainties left room for doubt, room that few people thought to examine closely at first, because the association looked so natural, so consistent with everything astronomers had seen before. When something fits the pattern you expect, there's a powerful temptation to accept it and move on. The real test of any proposed association between a compact object and a supernova remnant requires something more rigorous than positional coincidence. It requires measuring how the compact object is actually moving through space and tracing that motion backward in time. If SGR 0501 plus 4516 was truly born in the explosion that created HB9, then rewinding its trajectory should carry it straight back to the remnant, arriving there at a time consistent with the remnant's estimated age. It's the same principle as forensic ballistics. If a bullet was fired from a particular gun, its path will trace back to the barrel of that gun. If the trajectory doesn't line up, the bullet came from somewhere else. This kind of measurement is called proper motion. Proper motion is the apparent shift in an object's position on the sky over time, caused by the object's real physical movement through space. For distant objects like neutron stars, these shifts are incredibly tiny, measured in thousandths of an arc second per year. An arc second is a minuscule angular measurement. There are 3,600 of them in a single degree. The full moon spans about 1,800 arc seconds across the sky. The annual proper motions of typical neutron stars are just a few thousandths of that. Detecting such a small shift requires the sharpest instruments in all of astronomy, observations spread over months or years, and painstaking care to separate the object's true motion from every other effect that might shift its apparent position. Foreground stars moving independently, systematic biases in the telescope's optics, the orbital motion of Earth itself, which causes nearby objects to appear to wobble against the distant background in an effect called parallax. Measuring proper motion at this level of precision is among the most demanding work in observational science. This is where instruments like the Hubble Space Telescope become essential. Hubble, orbiting above the blurring effects of Earth's atmosphere, can pin down the positions of faint objects with extraordinary accuracy, measuring shifts so small that they would be completely invisible from any ground-based observatory. And this is exactly what a team of astronomers set out to do with SGR 0501 plus 4516. They aimed Hubble's sharp eye at the magnetar and began tracking its position across the sky with the kind of precision that only space-based instruments can deliver. What they found when they traced the magnetar's trajectory backward through time was not what anyone expected. The motion of SGR 0501 plus 4516 did not point back toward HB9. The trajectory missed the remnant. It didn't come close enough for the association to hold up under careful scrutiny. And the magnetar's path didn't trace back convincingly to any other obvious supernova remnant in the surrounding region either. There was no clear birthplace, no remnant waiting at the end of the rewound trajectory, No supernova crime scene matching the forensic evidence. The assumed connection, the tidy story that seemed so natural when the magnetar was first discovered, turned out to be far more fragile than it appeared. And once that link was broken, once the expected birthplace was seriously called into doubt, a much deeper and more unsettling question rose to the surface. If this magnetar didn't come from HB9, then where did it come from? Is there a supernova remnant out there that we simply haven't found yet? One that faded beyond detection or hides in a direction nobody has examined closely enough? Or is it possible, genuinely possible, that this magnetar was never born in a conventional supernova at all? That question, and the extraordinary possible answers it opens up, is what makes this magnetar one of the most fascinating objects in modern astrophysics. Because if a magnetar can form without a massive star dying in a conventional core collapse supernova, then our understanding of how the universe builds its most extreme objects needs serious revision. Something far stranger must have created this thing. And the candidates, from colliding neutron stars to collapsing white dwarfs, are as extraordinary as the magnetar itself. Part 2. Rewinding the bullet. To fully appreciate just how seriously astronomers take that finding, and why it's considered robust enough to overturn years of assumption, you need to understand what goes into measuring the motion of something as faint and distant as a magnetar. This is not a simple observation where you point a telescope, snap a picture, and see an object racing across the sky. Nothing in deep space moves fast enough for that. This is work that pushes the absolute limits of measurement science, requiring the sharpest instruments humanity has ever built, observations spread over years, and analytical techniques refined across more than 3 centuries of increasingly precise sky watching. The branch of astronomy devoted to this kind of precision position measurement has a name: astrometry. It is among the oldest disciplines in all of science, and its story begins with a discovery that shattered one of humanity's most deeply held assumptions about the heavens. For most of human history, the stars appeared completely motionless. The ancient Greeks called them the fixed stars, a name that persisted for nearly 2,000 years. While the planets wandered visibly against the stellar background, shifting their positions from night to night and week to week, the stars themselves seemed permanently anchored to the celestial sphere. This made intuitive sense. If the stars were very far away, any real motion they possessed would produce angular shift far too small for the naked eye to detect. And for millennia, the naked eye was the only instrument available. So the stars appeared to stand still, and everyone assumed they did. That assumption held until 1718, when the English astronomer Edmund Halley performed what sounds like a remarkably simple exercise. He took the positions of several bright stars, as recorded in the ancient catalogue of the Greek astronomer Ptolemy, compiled around 150 AD, and compared them to the positions measured in his own time, roughly 1500 years later. What he found was startling. 3 of the most prominent stars in the sky, Arcturus, Sirius, and Aldebaran, had shifted noticeably from the positions Ptolemy had recorded. The displacements were small, less than a degree in each case, but they were unmistakable and could not be attributed to errors in Ptolemy's measurements. These stars had genuinely moved. This discovery was profound in ways that extended far beyond just stellar cartography. It meant the sky was not a static backdrop. The stars were not fixed lanterns hanging at some immense distance. They were physical objects, each carrying its own velocity through three-dimensional space, each drifting on its own trajectory through the galaxy. The night sky you see tonight is not quite the same sky your ancestors saw, and the sky your distant descendants will see will be different still. The constellations are slowly changing shape, warping and distorting over timescales of tens of thousands of years as the stars that define them follow their independent paths. Given enough time, Orion will lose its familiar outline. The Big Dipper will bend and twist beyond recognition. Every pattern in the sky is temporary, a snapshot of a moment in a long, slow dance. Halley had discovered stellar proper motion, but detecting it through the crude method of comparing catalogues separated by 15 centuries was one thing. Measuring it precisely enough to reconstruct the trajectory of a specific object, to determine exactly where that object was thousands of years ago, that requires a completely different level of precision. And the numbers involved are almost absurdly small. In astronomy, angular positions on the sky are measured in degrees, arc minutes, and arc seconds. There are 360 degrees in a full circle, each divided into 60 arc minutes, each arc minute divided into 60 arc seconds. So 1 arc second represents 1/3,600,000th of the entire sky. It's a vanishingly small angle. To visualize it, imagine holding a single human hair at arm's length. The width of that hair, seen from that distance, spans roughly 1 arc second. Now consider that the typical annual proper motion of a star in our region of the galaxy is measured not in arc seconds, but in milliseconds. 1,000th of an arc second. Imagine that same human hair held at arm's length, but now you need to detect a shift equal to 1,000th the hair's width. That's the scale of measurement we're talking about. And for distant, faint objects like magnetars, the proper motions can be smaller still, sometimes just a few milliarc seconds per year. Detecting such impossibly tiny shifts requires not only extraordinary instruments, but also an entirely separate piece of information: distance. This is because what you actually observe when you measure a proper motion is an angular shift. How far the object appears to move across the sky per unit of time. But the same physical velocity will produce very different angular motions depending on how far away the object is. An airplane flying overhead at high altitude appears to drift slowly across the sky, even though it's traveling at hundreds of kilometers per hour. A bird flying past your window at a fraction of that speed appears to streak across your field of view. The bird is slower in absolute terms, but it's much closer, so its angular motion is larger. The same principle applies to stars and neutron stars. To convert an observed angular shift into a real physical velocity through space, measured in kilometers per second, you need to know the distance to the object. Without distance, a measured proper motion is ambiguous. You can't tell whether you're looking at a fast object far away or a slow object nearby. And measuring distance to astronomical objects is genuinely hard. For nearby stars, within a few thousand light years, astronomers rely on a technique called parallax. As Earth orbits the Sun over the course of a year, our vantage point shifts. We view the universe from slightly different positions 6 months apart, separated by roughly 300 million kilometers, the diameter of Earth's orbit. A star that's relatively close to us will appear to shift back and forth against the far more distant background stars, the same way a nearby lamppost appears to jump sideways against the distant mountains when you take a step to the left or right. By measuring the angle of that apparent shift, the parallax angle, you can use straightforward geometry to calculate the distance. The first successful measurement of stellar parallax was achieved in 1838 by the German astronomer Friedrich Bessel. He targeted a faint star called 61 Cygni in the constellation Cygnus, and, through months of meticulous observation, detected a parallax angle of about 1/3 of an arc-second. That tiny angle translated to a distance of roughly 10.3 light-years. It was a monumental achievement, the first time a stellar distance had been directly and reliably measured. But it also demonstrated just how minuscule these angles truly are. Even the nearest star system to our Sun, Alpha Centauri, shows a parallax of only about 3/4 of an arc-second. More distant objects have even smaller parallaxes. A star 1,000 light-years away shows a parallax of roughly 3 milliarcseconds. An object several thousand light-years away, the distance range where SGR 0501 plus 4516 likely resides, shows a parallax so small that measuring it from the ground becomes nearly impossible. The reason ground-based telescopes struggle with these measurements comes down to something every astronomer knows intimately: Earth's atmosphere. The air above us is in constant turbulent motion, swirling and churning in cells of slightly different temperature and density. As starlight passes through this turbulence, its path gets bent slightly in different directions and by different amounts from moment to moment. This is why stars twinkle. It looks beautiful to the naked eye, but for precision astrometry, it's a nightmare. The turbulence smears out pinpoint sources of light into fuzzy, dancing blobs, and the center of that blob shifts unpredictably from instant to instant. Even the finest ground-based observatories at the highest, driest, most stable sites on Earth can typically pin down a star's position to only about 50 to 100 milliseconds under excellent conditions. That's impressive by everyday standards, but it's nowhere near sufficient for tracking the motion of a faint neutron star, thousands of light years away, where the annual shift might be just a handful of milliseconds. The solution is to leave the atmosphere behind entirely. And this is exactly what the European Space Agency did. First with the Hipparcos satellite launched in 1989, and then with the far more powerful Gaia spacecraft launched in 2013. Hipparcos operated for roughly 3.5 years and measured the positions, parallaxes, and proper motions of about 118,000 stars with a precision of about 1 millisecond. This was revolutionary, an improvement over ground-based catalogs by a factor of 10 or more. For the first time, astronomers had a precise, self-consistent map of stellar positions and motions across a substantial portion of the solar neighborhood. But Gaia is something else entirely. Gaia took the principles behind Hipparcos and scaled them up to a degree that borders on the absurd. Instead of 100,000 stars, Gaia is surveying nearly 2 billion objects across the entire sky. Its positional precision for bright stars reaches roughly 20 to 25 micro-arcseconds. A micro-arcsecond is a millionth of an arcsecond. To grasp how small this is, imagine a coin lying on the surface of the moon. 20 micro-arcseconds is roughly the angular size of that coin as seen from Earth. Gaia can detect positional shifts that small. The mission's third major data release, published in 2022, provided positions, parallaxes, and proper motions for over 1.5 billion sources, creating the most detailed three-dimensional map of our galaxy ever constructed. It revealed the orbits of stars around the galactic center, the internal motions of star clusters, the tidal streams left behind by galaxies being shredded by the Milky Way's gravity. Gaia has shown us the galaxy as a dynamic, living structure full of motion at every scale. Yet even Gaia has its limits. The spacecraft excels at bright, isolated sources scattered across open regions of the sky, but a faint magnetar embedded in a complex field, surrounded by the diffuse glow of interstellar gas and potentially blended with other sources at similar distances, presents a much harder target. For objects like SGR 0501 plus 4516, where you need the sharpest possible resolution on a specific faint source, rather than a broad survey of bright stars, a different tool becomes essential: the Hubble Space Telescope. Hubble was not designed primarily for astrometry. Its core mission has always been deep imaging and spectroscopy, capturing detailed portraits of galaxies, nebulae, and other cosmic structures. But Hubble's extraordinary angular resolution, its ability to produce sharp, undistorted images free from atmospheric blurring, makes it an unexpectedly powerful astrometric instrument for targeted observations of individual faint objects. The technique it employs for this kind of work is called differential astrometry, and it's a clever approach that sidesteps several of the challenges that make absolute position measurements so difficult. The idea works like this. You take an image of the target, the magnetar, along with everything else that falls within the same camera field. Many of those other objects are distant background galaxies, millions or even billions of light years away. Because these galaxies are so incredibly far away, their own proper motions are effectively zero. They don't move perceptibly on the sky over the timescales of your observations. They serve as fixed reference points, an unchanging coordinate grid printed on the sky behind your target. You take one image and carefully measure the position of the magnetar relative to these reference galaxies. Then you wait months, ideally years. You take another image with the same instrument, the same detector, the same optical configuration. Then you compare the two images, measuring how far the magnetar has shifted relative to the reference galaxies. Because you're measuring relative positions rather than absolute ones, many systematic effects cancel out. Any drift in the telescope's pointing, any subtle change in the optics, anything that shifts all objects in the frame by the same amount simply drops out of the measurement. What remains is the magnetar's true motion against the fixed background of the distant universe. With careful calibration and multiple epochs of observation, Hubble can achieve astrometric precision of roughly 1/10 to 2/10 of a millisecond per epoch. That's sharp enough to detect the crawl of a compact object thousands of light years away. But before we can use that measured motion to reconstruct a trajectory, there's one more piece of physics to understand. Natal kicks. When a neutron star is born in a supernova, the explosion is almost never perfectly symmetric. Slight asymmetries in how the core collapses, in how neutrinos stream outward from the proto-neutron star, in how the shock wave interacts with the falling outer layers, all conspire to deliver a net push to the newborn compact object in one direction. This push, applied in a fraction of a second during the most violent moments of the explosion, launches the neutron star out of the debris field at high speed. Astronomers call this a natal kick, and these kicks can be enormous. Typical natal kick velocities range from about 100 to several hundred kilometers per second, and some neutron stars appear to have received kicks exceeding 1,000 kilometers per second. At 400 kilometers per second, a neutron star covers roughly 1 light year every 750 years. That means over the course of 10,000 years, it will have traveled more than 13 light years from the site of the explosion that created it. This displacement is the whole basis of trajectory reconstruction. The neutron star is no longer sitting at its birthplace. It has traveled a measurable distance in a specific direction, and if you can determine that direction and speed precisely enough, you can trace its path backward through time and identify where it was born. The logic is like rewinding a security camera. If you can see where someone is standing and which direction they're walking, you can run the footage backward and figure out which door they came through. For a magnetar born in a supernova, running the trajectory backward should carry it straight back to the supernova remnant, arriving there at a time consistent with the remnant's estimated age. If both conditions are met, position and timing, the connection between the magnetar and the remnant is considered secure. A dedicated team of researchers carried out exactly this test for SGR 0501 plus 4516. Using Hubble's Wide Field Camera 3, one of the telescope's most sensitive imaging instruments, they observed the magnetar at multiple epochs separated by enough time for the proper motion to accumulate into a measurable displacement. The work demanded extraordinary care. The magnetar is faint, far fainter than the bright, well-studied stars that populate most astrometric catalogues. Its signal had to be painstakingly extracted from the complex background of the surrounding sky region. The positions of reference sources, those fixed background galaxies serving as the measurement grid, had to be determined with the highest achievable accuracy. Subtle instrumental effects, tiny distortions in the camera's optics, small variations in how light falls on the detector, all had to be modeled and corrected. Multiple observations were combined statistically to beat down the noise, squeezing every last fraction of a milliarc second of precision from the data. This is not the kind of measurement that happens quickly. It takes years of planning, observation, and meticulous analysis, but the result was clear. When the team took the measured proper motion and projected the magnetar's trajectory backward in time, the path did not pass through the center of HB9. It didn't pass through any part of HB9 that would be consistent with the magnetar having been born there. The direction of the magnetar's motion on the sky simply doesn't align with an origin inside that remnant. Running the clock backward, following the magnetar's path in reverse at its measured velocity, carries it through a region of sky that doesn't coincide with HB9's boundaries at any plausible time. The association that had looked so natural, so obvious when the magnetar was first discovered, a young magnetar sitting right next to a supernova remnant in the same patch of sky, failed the most rigorous test astronomers could apply to it. And the margin of failure mattered. This wasn't a case where the trajectory missed by some hair-thin amount that might be explained by measurement uncertainty. The researchers accounted for the uncertainties in their proper motion measurement. They considered the full range of possible trajectories allowed by those uncertainties. Even when they allowed the trajectory to shift within the bounds of the error bars, the backward path didn't convincingly intersect HB9 at the right time. The measurement was precise enough, and the miss was large enough that the association could no longer be defended as anything more than a coincidence of position on the sky. two objects that appear nearby in projection but are not physically related. This result carried real weight within the compact object community. It wasn't a minor refinement or a marginal correction to an existing model. It was a clean negative result on a question that most researchers had considered essentially answered the moment the magnetar was discovered. For years, the association between SGR 0501 plus 4516 and HB9 had been treated as settled background knowledge, the kind of fact that gets stated in introductory paragraphs without further justification. Papers cited it. Reviews mentioned it. It had become part of the furniture. And now the furniture had been pulled out from under the room. What made the result particularly difficult to dismiss was the nature of the measurement itself. Proper motion is not a model-dependent quantity. It's not derived from assumptions about how magnetars form or how remnants evolve. It's a direct observation of where the object is and how it's moving. You can argue about what the motion means, you can debate the implications, but you can't argue that the object is moving in a direction it isn't moving in. The trajectory goes where it goes, and this one didn't go to HB9. That left astronomers in an unusual position. They had a young, actively bursting magnetar with no confirmed birthplace. Not a magnetar whose birthplace was ambiguous or debated. A magnetar whose most obvious candidate birthplace had been actively, measurably excluded by the best astrometric data available. Once HB9 was eliminated, the natural next step was to search for alternative birthplaces. Perhaps the magnetar came from a different supernova remnant, one that was fainter or less well studied, located in a nearby but distinct direction. Perhaps it originated from a massive stellar cluster or an OB association, a loose grouping of young, hot, massive stars whose members are born together and gradually drift apart. If any such structure lay along the magnetar's backward trajectory, it could represent the true birth site. The astronomers searched. They examined the surrounding region of sky, comparing the magnetar's rewound path against catalogues of known supernova remnants, stellar associations, and clusters of massive stars. They considered objects at various distances, since the distance to the magnetar itself carries significant uncertainty. They explored a range of possible ages. Since the magnetar's characteristic age, an estimate based on how rapidly its spin is slowing down, is only an approximation that could differ substantially from its true age. They cast a wide net, looking for any structure that the trajectory might plausibly intersect at a time consistent with the magnetar's formation. They found nothing compelling. No supernova remnant sat convincingly along the backward path. No prominent cluster of massive stars appeared at the right position and distance. No OB association offered a plausible origin. The magnetar's trajectory, followed backward through time, simply runs into empty sky. Whatever structure once existed at the point of the magnetar's birth, if such a structure ever existed at all, has either faded beyond the limits of current detection, lies in a direction or at a distance that doesn't match the magnetar's motion, or was never there in the first place. This is a genuinely uncomfortable result for any astrophysicist who works on compact objects. Every formation theory, every model of how neutron stars and magnetars come into existence begins with the same premise. A massive star exhausts its fuel, its core collapses, a supernova explodes outward while a neutron star or magnetar remains behind, and the expanding remnant marks the site of that birth for thousands of years afterward. The remnant is the receipt, the proof of purchase. the forensic evidence linking the compact object to its origin. Without it, you have a magnetar with no apparent past, an object whose very existence demands a violent origin, hanging in the sky with no clear evidence of the violence that should have created it. There are cautious, conservative explanations for this. Perhaps the supernova remnant has simply faded below the threshold of detection. Remnants don't last forever. They expand, thin out, cool, and eventually merge indistinguishably into the general interstellar medium. If the magnetar is older than its characteristic age suggests, and characteristic ages can be misleading, then the remnant could have had enough time to dissipate entirely. Alternatively, the supernova might have occurred in a region of unusually low density interstellar gas, where the expanding debris encountered so little resistance that it thinned out and faded far more quickly than typical remnants do. These scenarios preserve the standard formation story. They explain the absence of a remnant without requiring any fundamentally new physics. But they raise their own questions. If the magnetar is significantly older than its characteristic age implies, then its magnetic field has been decaying for longer than expected, and the physics governing that decay might need revision. If the supernova occurred in an extremely sparse environment, it becomes a matter of coincidence that this particular magnetars happened to form in one of the emptiest regions nearby. Possible, certainly, but not entirely satisfying. And then there's the other possibility, the one that scientists had rarely needed to consider seriously before, because every other magnetar had fit the standard story well enough. What if SGR-0501 plus 4516 was never created by a conventional supernova? What if its origin lies in a completely different kind of event? One that doesn't leave behind the large, luminous, long-lived remnant that astronomers have learned to expect? What if the forensic evidence is missing not because it faded away, but because it was never there to begin with? This question is not rhetorical. There are real, physically grounded formation channels that could produce a magnetar without a conventional core collapse supernova. They involve processes that are far rarer and far stranger than the standard pathway, events that have been theorized for decades but never directly confirmed as magnetar factories. And the evidence from SGR-0501 plus 4516, this magnetar with no obvious birthplace, might be the first serious observational hint that these alternative channels actually operate in nature. Part 3, a magnetar. Without an explosion? Before we explore the stranger possibilities, we need to be honest about what the evidence actually shows and what it doesn't show. Because there's a crucial distinction that's easy to lose in the excitement of a mystery, and getting this wrong can lead to conclusions that go far beyond what the data supports. The Hubble measurements demonstrate that SGR-0501 plus 4516 is not traveling away from HB9. The trajectory doesn't trace back to that remnant. That finding is robust and well established. But here's what it does not demonstrate. It does not prove that no supernova ever happened. The absence of a visible remnant along the backward trajectory is not the same thing as proof that no explosion occurred. These are very different claims, and confusing them would be a serious scientific error. Supernova remnants are not permanent structures. They are temporary features, glowing shells of hot gas that expand outward from the explosion site, sweep up surrounding interstellar material, and gradually thin out as they spread across ever larger volumes of space. A typical supernova remnant is visible for somewhere between 20,000 and 100,000 years, depending on the energy of the original explosion, the density of the surrounding medium, and what wavelength of light you're observing in. After that, the remnant merges with the general interstellar gas and becomes undetectable. It doesn't vanish in any dramatic sense. The material is still there, still carrying the chemical signatures of the explosion, still enriching the surrounding region with heavy elements, but it becomes so diffuse, so spread out, so indistinguishable from the ordinary gas between stars that no telescope can pick it out as a separate structure anymore. Think of it like dropping ink into a bathtub full of water. At first, the ink is concentrated. You can clearly see the cloud of color expanding outward from the point where you dropped it. But as the ink disperses, the color fades. Eventually, the ink is so thoroughly mixed into the surrounding water that you can't tell it was ever there. The molecules of ink haven't disappeared. They're still present, distributed evenly throughout the tub. But the structure, the visible cloud, is gone. Supernova remnants undergo the same basic process, just on a scale of light years rather than bathtubs. This matters enormously for SGR 0501 plus 4516, because it means there's a perfectly conventional explanation for why no remnant is visible along the magnetar's backward path. If the magnetar is older than its characteristic age suggests, there may have been plenty of time for the remnant to dissipate beyond detectability. And characteristic ages, the estimates derived from how rapidly a magnetar's spin is slowing down, are known to be unreliable in many cases. Characteristic age assumes that the magnetar was born spinning much faster than it currently spins, and that it has been slowing down at a steady, predictable rate ever since. But these assumptions can be wrong. If the magnetar was born spinning more slowly than the model assumes, or if its spin-down rate has changed over time due to the evolution of its magnetic field, the characteristic age could substantially underestimate or overestimate the true age. The magnetic fields of magnetars are not static. They decay over time, and this decay is not necessarily smooth or predictable. Intense internal heating from field decay can alter the star's structure, which in turn affects how the magnetic field interacts with the star's rotation. The spin-down rate can change. The relationship between current spin period and age can become complicated. For some magnetars, the characteristic age is thought to be reasonably accurate. For others, it could be off by a factor of several. If SGR 0501 plus 4516 is genuinely older than its characteristic age implies, perhaps 50,000 years old rather than 10 or 20,000, then any supernova remnant created at its birth would have had ample time to fade below the threshold of detection. A remnant 50,000 years old, expanding into a region of average interstellar density, would be extremely faint, enormously spread out, and very difficult to distinguish from the surrounding interstellar medium even with modern instruments. This scenario preserves the standard formation story entirely. The magnetar was born in a normal core collapse supernova, received a natal kick that sent it flying, and the remnant has simply had enough time to vanish. There's another conservative possibility. Perhaps the supernova occurred in a region where the surrounding interstellar gas was unusually thin. The brightness and longevity of a supernova remnant depend critically on how much material the expanding shockwave encounters. In a dense region, the remnant sweeps up lots of gas, compresses it, heats it, and glows brightly for tens of thousands of years. But in a sparse region, a pocket of space where the interstellar gas density is well below average, the remnant expands freely without encountering much resistance. It thins out faster, cools faster, and fades from view much sooner. If the supernova that created this magnetar happened to go off in one of these low-density pockets, the remnant could have dissipated in a fraction of the time it would take in a denser environment. Again, this preserves the standard picture. No new physics is required, just an unlucky combination of circumstances that erase the evidence. These explanations are entirely plausible. They might even be correct. But they're also somewhat unsatisfying, because they rely on specific circumstances that are possible but not independently confirmed. We don't have direct evidence that the magnetar's characteristic age is wrong by a large factor. We don't have direct evidence that a supernova occurred in a low-density pocket along the backward trajectory. These are rescue hypotheses, explanations invoked to save a preferred theory when the straightforward prediction of that theory has failed. Rescue hypotheses aren't wrong by definition. Sometimes they turn out to be correct. But when multiple rescue hypotheses are needed to maintain a standard model, it's worth asking whether the standard model is really the best explanation or whether something more fundamental is going on. And this is where the story takes its most fascinating turn, because there are real, physically grounded mechanisms that could produce a magnetar without a conventional massive star core collapse supernova. These are not speculative fantasies. They're predictions of well-established physics, discussed in theoretical astrophysics for decades, but extremely difficult to confirm observationally because they're expected to be rare and to produce signals very different from ordinary supernovae. If any of these alternative channels actually operate in nature, SGR 0501 plus 4516 could be one of the first observational hints. The first alternative is neutron star merger formation. This one sounds dramatic because it is dramatic. Imagine two neutron stars locked in a tight binary orbit, circling each other at tremendous speed, spiraling slowly inward over millions or billions of years as they radiate energy away in the form of gravitational waves. Gravitational waves are ripples in the fabric of space-time itself, predicted by Einstein's general theory of relativity. Every pair of orbiting massive objects produces them, but the effect is usually immeasurably tiny. For two neutron stars in a closed binary, however, the gravitational wave emission is significant enough to gradually drain energy from the orbit, causing the two objects to drift closer together, orbit faster, emit even more gravitational waves, and spiral inward at an accelerating rate. This inspiral takes an enormously long time. For a typical pair of neutron stars born in a binary system, the time from formation to merger can be anywhere from tens of millions to billions of years. But eventually, inevitably, the two neutron stars draw close enough that tidal forces begin to tear at their surfaces. In the final seconds of the inspiral, the objects are orbiting each other hundreds of times per second, whipping around their common center of gravity at a significant fraction of the speed of light. And then they collide. Two objects, each containing more mass than our sun compressed into spheres 20 kilometers across, smash together at velocities approaching a third of the speed of light. The energy released is staggering. In gravitational waves alone, a neutron star merger radiates more energy in a fraction of a second than the sun will produce over its entire 10 billion year lifetime. The collision generates temperatures of hundreds of billions of degrees. Matter is flung outward in all directions. Heavy elements, including gold, platinum, and uranium, are forged in the extreme conditions through a process called rapid neutron capture, where atomic nuclei are bombarded by free neutrons so quickly that they absorb many neutrons before they have time to decay. This is one of the primary sources of the heaviest elements in the universe. We know neutron star mergers happen because we've observed one directly. On August 17th, 2017, the LIGO and Virgo gravitational wave detectors picked up a signal designated GW170817. The signal had the distinctive chirp pattern of two compact objects spiraling together, and the masses involved were consistent with two neutron stars. Within 2 seconds of the gravitational wave signal, NASA's Fermi satellite detected a short gamma-ray burst from the same region of the sky, and within hours, telescopes around the world identified a new point of light in a galaxy about 130 million light-years away. This optical counterpart, called a kilonova, faded over the following days and weeks as the radioactive heavy elements produced in the merger decayed and cooled. It was one of the most comprehensively observed events in the history of astronomy, confirming decades of theoretical predictions about what happens when neutron stars collide. But here's the question that matters for our story. What's left behind after the merger? The combined mass of two neutron stars typically exceeds the maximum mass that a single neutron star can support, a limit that depends on the still uncertain equation of state of ultra-dense matter, but is thought to be somewhere around 2 to 2.5 solar masses. So you might expect the merger product to immediately collapse into a black hole, and in many cases that's probably exactly what happens. The two neutron stars merge, briefly form a hypermassive or supramassive neutron star that exists for milliseconds to seconds and then collapses into a black hole, but not always. If the two merging neutron stars are on the lighter side, or if the merger dynamics are just right, the product might be a stable or long-lived neutron star rather than a black hole. The rapid rotation of this newly formed object, spinning at perhaps 1,000 revolutions per second from the angular momentum of the inspiral, can provide additional centrifugal support against gravitational collapse, allowing it to survive where a non-rotating object of the same mass would not. And the conditions inside this violently born, rapidly spinning remnant are exactly the kind of environment where a magnetar-strength magnetic field could be generated. The extreme temperatures, the violent convective churning, the rapid differential rotation, all the ingredients for the dynamo mechanism that Duncan and Thomson described are present, perhaps even more intensely than in a conventional supernova core collapse. To understand why the post-merger environment might be so effective at generating magnetar-strength fields, it helps to look more closely at what the first few seconds after a neutron star merger actually look like. Because the newly formed object is not simply a bigger, heavier version of an ordinary neutron star. It's something far more chaotic and far more extreme. In the immediate aftermath of the collision, the merger product is what physicists call a hypermassive neutron star. This is an object whose total mass exceeds the maximum that a uniformly rotating neutron star could support. It survives, at least temporarily, because it isn't rotating uniformly. Different layers of the object are spinning at different speeds. The core might be rotating at one rate, while the outer layers whip around at a significantly different rate. This differential rotation provides extra centrifugal support, holding the object up against gravitational collapse through a combination of rotation and thermal pressure that wouldn't be available to a cold, uniformly spinning neutron star of the same mass. But this configuration is inherently unstable. The differential rotation dissipates over time as internal friction and magnetic forces work to bring the different layers into alignment. As the differential rotation fades, the extra support disappears. If the object is too massive, It collapses into a black hole within milliseconds to seconds. The window of survival is razor thin. However, if the total mass is low enough, or if enough material is flung away during the merger to reduce the remnant's mass below the critical threshold, the object can transition from a hypermassive neutron star to a supramassive one, supported by uniform rapid rotation alone, and potentially to a stable neutron star if the mass falls within the permanently sustainable range. This transition, this survival through the critical window, is where the Magnetar connection becomes compelling. During those first violent seconds, while the remnant is still differentially rotating, the conditions for magnetic field amplification are extraordinary. The shearing between layers of ultra-dense fluid moving at different velocities stretches and twists magnetic field lines with tremendous force. This is the Kelvin-Helmholtz instability and the magneto-rotational instability working together, wrapping field lines tighter and tighter, amplifying weak seed fields by many orders of magnitude in a matter of seconds. Numerical simulations of neutron star mergers consistently show this magnetic amplification occurring. Starting from even modest initial fields, the merger dynamics can boost the magnetic field to strengths approaching or exceeding 100 trillion Gauss within the first few tens of milliseconds. If the remnant survives the critical window and settles into a long-lived state, it could emerge with a magnetar strength field already imprinted. Not generated by the slow dynamo mechanism that operates in conventional supernovae, but forged almost instantaneously in the violent rotational shearing of the merger itself, a different mechanism arriving at a similar destination, and crucially, one that leaves behind no supernova remnant to mark its origin. So neutron star mergers could, in principle, produce magnetars. The resulting object would have no conventional supernova remnant associated with it because no massive star exploded. The merger ejector, the material flung outward during the collision, is far less massive than the debris of a supernova. It amounts to perhaps a few percent of a solar mass, compared to the several solar masses ejected in a typical core collapse supernova. This material expands and disperses quickly, becoming undetectable within years to decades, rather than the thousands of years a supernova remnant persists. Any magnetar born through this channel would appear to have no remnant, no birthplace, no forensic evidence of the event that created it. By the time astronomers noticed it through its X-ray or gamma-ray emissions, the merger debris would have long since vanished into the interstellar background. Could SGR 0501 plus 4516 be the product of such a merger? It's possible, but this hypothesis carries its own challenges. Neutron star mergers are expected to be rare. The inspiral time is long, and not all binary neutron star systems are in configurations that lead to merger within the age of the universe. The rate of neutron star mergers in the Milky Way is estimated at perhaps 1 every 10,000 to 100,000 years. That's not zero, but it's much rarer than core collapse supernovae, which occur roughly twice per century in a galaxy like ours. The chance of a specific magnetar being a merger product is therefore low, though not negligible. There's also the question of whether a merger remnant can survive long enough and maintain a strong enough magnetic field to be detected as a magnetar thousands of years later. The theoretical models say yes, under the right conditions, but the details remain uncertain. No magnetar has been conclusively identified as a merger product. So we're in the realm of theoretical plausibility rather than observational confirmation. The second alternative formation channel is arguably even more intriguing. Accretion-induced collapse of a white dwarf. To understand this process, we need to go back to how white dwarfs form and what limits their existence. When a star like our Sun reaches the end of its life, it swells into a red giant, sheds its outer layers, and leaves behind a white dwarf. A white dwarf is the exposed core of the dead star, extremely hot initially but slowly cooling over time. It's composed mainly of carbon and oxygen, the products of helium fusion that occurred during the star's red giant phase. It's roughly the size of Earth, but contains about half to slightly less than one solar mass worth of material. White dwarfs are supported against gravitational collapse, not by nuclear fusion, which has ceased, but by a quantum mechanical effect called electron degeneracy pressure. This is a fundamental consequence of the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state simultaneously. When matter is compressed to the density found inside a white dwarf, the electrons are squeezed so tightly together that this quantum mechanical restriction creates an outward pressure that resists further compression. As long as the white dwarf's mass stays below a critical threshold, electron degeneracy pressure is sufficient to hold it up. That critical threshold was calculated in 1930 and 1931 by the Indian-American astrophysicist Subramanian Chandra Sekhar. He showed that electron degeneracy pressure can support a white dwarf only up to a mass of about 1.4 solar masses. Beyond this limit, now called the Chandrasekhar limit in his honor, the electron simply cannot push back hard enough to resist gravity. The white dwarf must collapse. Now, most white dwarfs are born with masses comfortably below the Chandrasekhar limit, typically between about half and one solar mass. They sit quietly in space, slowly cooling, harming nothing, perfectly stable. But some white dwarfs are not alone. Many exist in binary systems, orbiting a companion star. And if that companion is close enough, something remarkable can happen. As the companion star evolves and swells, material from its outer layers can spill across the gravitational boundary between the two stars and fall onto the surface of the white dwarf. This process is called accretion, and it gradually adds mass to the white dwarf, ounce by ounce, year by year, century by century, slowly pushing it toward the Chandrasekhar limit. What happens when a white dwarf reaches the limit depends on its composition and the rate at which mass is being added. In the scenario most people have heard of, the white dwarf crosses the threshold and ignites a thermonuclear explosion. The carbon and oxygen in its interior, compress to extreme densities, undergo runaway nuclear fusion. The entire white dwarf is consumed in a colossal explosion called a Type 1a supernova. Nothing is left behind. No neutron star, no black hole. The white dwarf is completely obliterated, its entire mass converted into an expanding cloud of radioactive debris. Type 1a supernovae are among the brightest events in the universe and are used as standard candles for measuring cosmic distances. They played a crucial role in the discovery that the universe's expansion is accelerating. But there's another possibility, one that's less well known, but potentially far more relevant to our story. The reason composition matters so much comes down to a subtle but critical difference in nuclear physics that determines whether the white dwarf explodes or collapses. Not all white dwarfs are made of the same material. Their composition depends on how massive the original star was before it died. Stars in the lower part of the intermediate mass range, roughly 1 to about 6 solar masses, go through hydrogen and helium fusion in their cores, but never get hot enough to ignite carbon. When these stars shed their outer layers and die, they leave behind white dwarfs composed primarily of carbon and oxygen. These are the most common type of white dwarf in the galaxy. But stars in a slightly higher mass range, roughly 6 to 8 solar masses, though the exact boundaries are still debated, undergo an additional fusion stage before they die. Their cores get hot and dense enough to ignite carbon, fusing it into a mixture of oxygen, neon, and magnesium. When these heavier intermediate mass stars shed their outer layers, they leave behind white dwarfs with this different composition. Oxygen, neon, magnesium white dwarfs are rarer than their carbon-oxygen cousins, but they exist in significant numbers throughout the galaxy. The distinction between these two compositions is what separates a thermonuclear explosion from a gravitational collapse. When a carbon-oxygen white dwarf is pushed to the Chandrasekhar limit, the carbon in its interior can ignite in a runaway thermonuclear reaction. Carbon fusion at extreme densities is violently unstable. Once it starts, it can't be stopped. The fusion front races through the entire white dwarf in seconds, releasing enough energy to completely unbind the star. The result is a Type 1a supernova, and nothing solid remains behind. But oxygen, neon, magnesium white dwarfs respond differently to the same squeeze. At the extreme densities reached near the Chandrasekhar limit, something else happens before fusion can run away. The electrons in the material, the same electrons whose quantum mechanical pressure has been holding the white dwarf up, begin to be captured by the neon and magnesium nuclei. This process, called electron capture, is a nuclear reaction in which a high-energy electron is absorbed by a proton inside a nucleus, converting the proton into a neutron and releasing a neutrino. Each electron capture event removes one electron from the population that was providing degeneracy pressure support. As more and more electrons are captured, the pressure drops. The white dwarf doesn't explode. It loses its support structure from the inside out. The collapse, when it comes, is gravitational rather than thermonuclear. The entire white dwarf implodes inward, compressing itself into a neutron star, in a process that is physically closer to the core collapse of a massive star than to a Type 1a supernova. Instead of igniting a thermonuclear explosion that destroys the entire star, the white dwarf undergoes a quiet, rapid gravitational collapse. This process is called accretion-induced collapse, and it differs from a conventional core collapse supernova in several critical ways that are directly relevant to the puzzle of SGR 0501 plus 4516. First, the energy released in an accretion-induced collapse is far smaller than in a typical core collapse supernova. A core collapse supernova involves the gravitational potential energy of an iron core roughly 1.5 solar masses in size, plus the kinetic energy of several solar masses of infalling material, producing a total energy release on the order of 10 to the 46 joules, most of it carried away by neutrinos. An accretion-induced collapse involves a less energetic implosion with far less material ejected outward. The optical display, if there is one at all, would be vastly fainter than a supernova. It might look more like a faint, fast-fading transient, easily missed by surveys unless they happen to be watching the right patch of sky at the right moment. Second, and crucially, the amount of material ejected in an accretion-induced collapse is tiny compared to a conventional supernova. In a core collapse supernova, several solar masses of the star's outer layers are blasted into space, creating a massive, long-lived remnant. In an accretion-induced collapse, the material available to be ejected is limited to whatever thin shell of matter sits on the surface of the collapsing white dwarf, plus perhaps a small amount of material unbound by the neutrino pulse. We're talking about hundredths of a solar mass at most. This small amount of debris expands, thins out, and becomes undetectable within decades to centuries, not millennia. By the time the resulting neutron star begins exhibiting magnetar behavior, bursting in X-rays and gamma rays, any remnant of the collapse event has long since disappeared. Third, accretion-induced collapse does not require a massive progenitor star. It requires a white dwarf in a binary system, a white dwarf that accumulated mass over millions of years from a companion. The progenitor star that originally produced the white dwarf could have been a relatively modest star, 3 to 8 solar masses, not the 8+ solar mass giants required for conventional core collapse supernovae. This means accretion-induced collapse can happen in stellar populations and environments where core collapse supernovae cannot. It can occur in older stellar populations where the massive stars have all died long ago, but binary white dwarf systems still persist. Fourth, the natal kick delivered to the neutron star in an accretion-induced collapse is expected to be much smaller than the kicks typical of core collapse supernovae. In a conventional supernova, asymmetries in the explosion can launch the neutron star at hundreds of kilometers per second. In an accretion-induced collapse, the implosion is more symmetric and the energy is lower, resulting in a gentler kick, perhaps only tens of kilometers per second. This is actually consistent with some of the motion characteristics observed in magnetars that don't quite fit the standard high kick picture. Though the proper motion of SGR 0501 plus 4516 alone cannot distinguish between formation channels based on velocity. The question of whether accretion-induced collapse can produce not just a neutron star, but specifically a magnetar with its extraordinarily amplified magnetic field, is still an active area of theoretical research. The conditions inside a collapsing white dwarf are different from those inside a collapsing iron core. The initial temperature, the composition, the angular momentum profile all differ. Whether the dynamo mechanism proposed by Duncan and Thompson can operate effectively in the accretion-induced collapse scenario depends on details of the collapse dynamics that are not yet fully resolved. But there's no fundamental reason it couldn't work. The basic ingredients, rapid rotation and vigorous convection in the first seconds of the neutron star's life, could plausibly be present. If accretion-induced collapse can produce magnetars, then SGR 0501 plus 4516 becomes a natural candidate. It would explain the absence of a detectable supernova remnant, because accretion-induced collapse doesn't produce one that lasts. It would explain why the magnetar's trajectory doesn't trace back to any known remnant or massive star cluster, because no massive star was involved. It would explain the object's existence without requiring any rescue hypotheses about faded remnants or low-density environments. The evidence would simply be consistent with a formation channel that doesn't leave the kind of forensic traces astronomers usually look for. But we need to be careful here. Accretion-induced collapse has never been directly observed with certainty. It's a theoretical prediction with strong physical motivation, but the observational evidence for it is circumstantial at best. We believe it should happen because the physics says it can. We have candidate events, unusual faint transients that might be accretion-induced collapses, but none has been conclusively identified. And we have never confirmed that accretion-induced collapse produces a magnetar specifically. The theoretical case is plausible, but not proven. This is where SGR 0501 plus 4516 sits in the scientific landscape, not as a solved case, but as a clue. A piece of evidence that doesn't fit the standard narrative cleanly and points toward possibilities that have been theorized, but never confirmed. It's not proof of accretion-induced collapse. It's not proof of merger formation. It's not even conclusive proof that no conventional supernova occurred. What it is a challenge. A magnetar that refuses to cooperate with the simple story. An object whose measured motion undercuts the obvious explanation and forces astronomers to take seriously the alternatives they had previously regarded as theoretical curiosities. And in science, that kind of challenge is worth its weight in gold, because it's precisely when comfortable assumptions are tested and found wanting that the most important discoveries happen. The most productive questions in science are rarely the ones with easy answers. They're the ones that resist easy answers, that force researchers to look in directions they wouldn't have chosen on their own, that pull apart a tidy explanation and reveal something messier and more interesting underneath. An anomaly is not a failure of understanding. It's an invitation to look deeper. And the sharper the anomaly, the more likely it is to lead somewhere genuinely new. SGR 0501 plus 4516 is stubborn. Its motion doesn't match HB9. Its trajectory doesn't lead back to any obvious birthplace. And the explanations for why range from the mundane, a faded remnant, an unreliable age estimate, to the extraordinary. A neutron star merger. An accreting white dwarf that crossed the threshold and collapsed. The truth could lie anywhere along that spectrum, and finding it will require exactly the kind of patient, precise, multi-wavelength investigation that modern astronomy excels at. Part 4. Why it matters. Everything we've discussed so far might seem like an isolated puzzle. One magnetar with a confusing backstory. An astronomical cold case that affects a handful of specialists who study compact objects. But the implications reach much further than a single object in the constellation Camelopardalis. If magnetars can form through channels other than core collapse supernova, it changes how we interpret some of the most mysterious signals the universe sends us. And among those signals, none has generated more excitement and more confusion over the past 2 decades than fast radio bursts. A fast radio burst is exactly what the name suggests. A burst of radio waves, incredibly brief, typically lasting only a few milliseconds, but astonishingly powerful. In those few milliseconds, a fast radio burst can release as much energy in radio waves as the sun produces across all wavelengths in an entire day, sometimes more. These bursts arrive from cosmological distances, often from galaxies billions of light years away, which means the actual energy involved is extraordinary. Whatever is producing them is channeling enormous amounts of power into a tight beam of radio emission on timescales shorter than the blink of a human eye. The first fast radio burst was discovered in 2007, buried in archival data from the Parkes Radio Telescope in Australia. It was a single pulse, appearing in a fraction of a second and then vanishing. At first, many astronomers were skeptical. One pulse in one dataset from one telescope could be an instrument glitch, a burst of terrestrial interference, anything. But over the following years, more bursts were found. Different telescopes, different parts of the sky, different times. The phenomenon was real. Something out there was producing these impossibly brief, impossibly powerful flashes of radio energy. What made fast radio bursts so puzzling was not just their power, but their diversity. Some appeared to be one-off events, a single burst from a given position on the sky, never repeating. Others turned out to be repeaters, sources that produced multiple bursts over days, weeks, or months, then sometimes went quiet, then burst again. The repeaters ruled out any explanation that destroyed the source, like a collision or an explosion, because the source had to survive to burst again. But the one-off events left open the possibility that at least some fast radio bursts might come from cataclysmic events, things that happen only once. For years, the community debated what could produce them. The list of proposed explanations grew long and sometimes exotic. Colliding neutron stars, collapsing cosmic strings, evaporating black holes, flaring magnetars, interactions between neutron stars and asteroid belts. Even in some speculative corners, alien transmissions. The problem was that fast radio bursts happened at such enormous distances that resolving the source was essentially impossible. All you had was a brief flash of radio waves, a rough direction on the sky, and very little else to work with. The breakthrough came on April 28th, 2020, when something extraordinary happened much closer to home. A magnetar in our own galaxy, designated SGR 1935 plus 2154, produced a burst that was detected simultaneously by multiple instruments. The Keim Radio Telescope in Canada and a survey instrument called STARE-2 both picked up an intense pulse of radio emission from the Magnetar's direction. The burst, designated FRB 200428, was thousands of times less energetic than the cosmological fast radio bursts observed from distant galaxies. But it was unmistakably a fast radio burst in character. Same millisecond duration, same radio frequency range, same dispersed signal structure, where lower frequency radio waves arrive slightly later than higher frequency ones, because they travel more slowly through the ionized gas between stars. And crucially, the burst coincided with an X-ray burst from the same magnetar. The magnetar was simultaneously releasing energy across multiple parts of the electromagnetic spectrum, exactly as theoretical models had predicted a magnetar-powered fast radio burst would behave. The X-ray burst confirmed the source. This wasn't an ambiguous detection from some unknown point in a distant galaxy. This was a known, catalogued magnetar in the Milky Way, caught in the act of producing a fast radio burst. This detection didn't prove that all fast radio bursts come from magnetars. The cosmological bursts are far more energetic than what SGR 1935 plus 2154 produced, and there's still debate about whether the same mechanism can scale up to explain the most powerful events observed from billions of light years away. Some researchers think the galactic detection represents the weaker end of a continuous spectrum of magnetar activity, with the most energetic bursts happening during the most extreme magnetic events. Others think there might be multiple source populations producing fast radio bursts through different mechanisms. The question is far from settled. But what the 2020 detection established beyond reasonable doubt is that magnetars can produce fast radio bursts. Magnetars are now the leading candidates for at least a substantial fraction of these events. And this is where the formation history of magnetars stops being an esoteric question about one unusual object and becomes central to one of the most active fields in modern astrophysics. Here's why. If all magnetars are born from core collapse supernovae, then fast radio bursts should be found predominantly in galaxies with active star formation. Core collapse supernovae happen only when massive stars die, and massive stars are short-lived. They form in regions of active star formation and die within a few million years, never straying far from the stellar nurseries where they were born. So core collapse supernovae, and the neutron stars and magnetars they produce, should be concentrated in young, star-forming regions of galaxies. If magnetars are the engines behind fast radio bursts, and if magnetars come exclusively from core collapse supernovae, then fast radio bursts should also cluster in star-forming regions. You should find them in the spiral arms of disk galaxies, in irregular galaxies with high star formation rates, in the kinds of environments where young, massive stars live and die, and indeed, many fast radio bursts have been localized to star-forming galaxies. This is consistent with the core collapse picture, but not all of them. Some fast radio bursts have been traced to galaxies with relatively low star formation rates. Some have been found in environments that don't obviously match the profile you would expect. If every magnetar came from a recently exploded massive star. A few have been localized to the outskirts of their host galaxies, far from any obvious concentration of young stars. These anomalous locations are individually explainable. Maybe the magnetar received a large natal kick and traveled far from its birthplace. Maybe the host galaxy's star formation history is more complex than it appears. But collectively, these outliers raise a question. As astronomers localize more fast radio bursts to specific host galaxies, mapping not just where the bursts come from, but what kind of stellar environment surrounds each source, the fraction appearing in unexpected locations keeps growing. It's no longer one or two anomalies that might be explained away individually. The sample is reaching a size where the collective pattern carries genuine statistical weight. And when a pattern emerges that a model doesn't predict, the model has to adapt. What if some of the magnetars producing fast radio bursts weren't born in core collapse supernovae at all? If magnetars can form through neutron star mergers, the demographics of fast radio bursts change significantly. Neutron star mergers don't require recent star formation. The two neutron stars in a merging binary were born in supernovae, yes, but the inspiral time, the time it takes for the binary to lose enough energy through gravitational-wave emission to finally merge, can be enormously long, hundreds of millions of years, even billions of years. By the time the merger actually happens, the binary system may have traveled far from the star-forming region where the original stars were born. It may have drifted into the outskirts of its host galaxy, or into a region with no ongoing star formation at all. A magnetar born from such a merger would appear in an environment that makes no sense under the core collapse-only model. It would be in the wrong place, the wrong kind of galaxy, or the wrong part of the right galaxy, and it would have no supernova remnant marking its origin. If magnetars can form through accretion-induced collapse of white dwarfs, the picture shifts even further. White dwarfs are the remnants of stars in the 1 to 8 solar mass range, stars far more common than the massive stars that produce core collapse supernovae. White dwarfs in binary systems can persist for billions of years before accretion pushes them over the Chandrasekhar limit. An accretion-induced collapse could happen in an old stellar population in an elliptical galaxy where star formation ceased billions of years ago in the halo of a spiral galaxy far from any spiral arm. A magnetar produced this way would appear in an environment utterly inconsistent with core collapse origins. It would be a smoking gun for an alternative formation channel. Finding fast radio bursts in these unexpected environments would therefore be powerful indirect evidence that magnetars can form through channels other than core collapse supernovae. Each fast radio burst localized to an old, quiescent galaxy or to the outskirts of a star-forming galaxy becomes a data point in this argument. Not proof on its own, but part of a growing body of evidence that the magnetar formation picture is more complex than the simple one-pathway model that dominated for decades. The implications extend beyond fast radio bursts. Alternative magnetar formation channels also matter for gravitational wave astronomy. When LIGO and Virgo detected GW170817 in 2017, it was a neutron star merger that produced a short gamma-ray burst and a kilonova. If some fraction of neutron star mergers also produce magnetars, then gravitational wave detectors might eventually observe the formation of a magnetar in real time. The gravitational wave signal from a merger that produces a stable magnetar would look subtly different from one that produces a black hole. The post-merger signal, the gravitational waves emitted after the two neutron stars have combined, would persist for longer in the magnetar case because the spinning, oscillating neutron star continues to emit gravitational waves for seconds or longer before settling down. Detecting this post-merger signal would be direct evidence that magnetars can form through mergers. Current gravitational wave detectors are not quite sensitive enough to reliably detect post-merger signals from neutron star mergers at typical distances. But the next generation of detectors, instruments planned for the 2030s and beyond, should be capable of it. When they come online, every neutron star merger they detect will be scrutinized for signs of a magnetar remnant. If magnetar formation through mergers is common enough, we'll see it directly in the gravitational wave data. Alternative formation channels also carry implications for heavy element production in the universe. Neutron star mergers are confirmed sources of rapid neutron capture elements, the heaviest elements on the periodic table, including gold, platinum, and uranium. If some mergers produce magnetars rather than black holes, the presence of a highly magnetized, rapidly spinning remnant could alter how much material is ejected and what elements are produced. The magnetar's enormous rotational energy could drive powerful winds that unbind additional material from the remnant, increasing the total mass of heavy elements produced. Alternatively, the magnetic field could collimate the outflow into jets, concentrating the ejector in specific directions. The nucleosynthetic yields, the amounts and ratios of different heavy elements produced, could differ between mergers that produce black holes and mergers that produce magnetars. Understanding which outcome is more common directly affects our models of how the heavy elements accumulate in the universe over cosmic time, including the heavy elements that ended up in the Earth and in us. Accretion-induced collapse has its own nucleosynthetic story. The small amount of material ejected during the collapse undergoes its own nuclear processing, producing a distinct set of isotopes that differs from both core collapse supernovae and neutron star mergers. If accretion-induced collapse occurs frequently enough, It contributes to the chemical evolution of galaxies in ways that aren't captured by models that consider only the standard formation channels. Every element on the periodic table has a story, a chain of nuclear reactions in specific astrophysical environments that produced it. Adding new formation channels for neutron stars and magnetars adds new chapters to their stories. So where does all of this leave SGR 0501 plus 4516? It remains what it has been since the Hubble measurements were published. A clue, not a conclusion. The proper motion data ruled out the association with HB9. The backward trajectory doesn't intersect any obvious supernova remnant or massive stellar cluster. The standard explanation that this magnetar was born in a conventional core collapse supernova and that we can simply point to the remnant and say, there, that's where it came from, does not work for this object. Something about its origin is unusual, but the precise nature of that unusual origin is not determined by the current evidence. It could be that a conventional supernova did occur, but the remnant has faded beyond detection due to age or environment. It could be that the magnetar is older than its characteristic age suggests, giving any remnant ample time to dissipate. These are boring explanations in the sense that they don't require new physics. But boring explanations are sometimes correct. Science doesn't owe us excitement. It owes us accuracy. Alternatively, SGR 0501 plus 4516 could be the product of a neutron star merger or an accretion-induced collapse, formed through a channel that doesn't produce a large, long-lived remnant. This would be far more consequential, opening a door to formation pathways that have been theorized but never observationally confirmed for magnetars. It would mean the universe builds its most magnetically extreme objects through more than one recipe, and that some magnetars appear in environments and at times and places where the standard model says they shouldn't. How could future observations distinguish between these possibilities? Several approaches are being pursued or planned. More precise, proper motion measurements accumulated over longer baselines of time will tighten the constraints on the magnetar's trajectory. The longer you watch a moving object, the more precisely you can determine its direction and speed. Additional epochs of Hubble observation or high-precision measurements from next-generation telescopes could rule out additional candidate birthplaces or reveal a trajectory consistent with an origin in a structure not yet identified. If the magnetar's path intersects a previously overlooked stellar association or a faint, extended remnant structure that current surveys have missed, the conventional picture could be restored. Deep radio and X-ray surveys of the region along the magnetar's backward trajectory could search for ultra-faint remnant signatures. A supernova remnant that has faded below the detection threshold of existing surveys might still be detectable with more sensitive instruments or at different wavelengths. The remnant might be visible as a faint shell of emission at very low radio frequencies, or as a subtle enhancement in the distribution of hot gas detectable in X-rays. Finding such a remnant would settle the question in favor of a conventional origin. Failing to find one, despite increasingly deep searches, would strengthen the case for an alternative channel. Improved distance measurements would also help enormously. The distance to SGR 0501 plus 4516 is currently uncertain, and this uncertainty propagates into everything else. The physical velocity derived from the proper motion, the age estimate, the region of space through which the magnetar has traveled, all depend on how far away it is. A more precise distance, perhaps from a future Gaia data release that includes improved parallaxes for stars in the surrounding field, or from direct radio parallax measurements, if the magnetar is bright enough at radio wavelengths, would sharpen every aspect of the trajectory analysis. Observations of other magnetars with similarly anomalous trajectories would also be transformative. If SGR 0501 plus 4516 is the only magnetar that doesn't trace back to an obvious remnant, it might simply be a statistical outlier, a standard magnetar that happened to form in circumstances that erase the evidence. But if multiple magnetars show the same pattern, if several objects across the sky all fail to point back to any obvious birthplace, that's much harder to explain away with case-by-case rescue hypotheses. It would suggest that an alternative formation channel is operating frequently enough to produce a detectable population. Systematic proper motion surveys of the full magnetar catalogue using Hubble, Gaia, and future facilities are the way to test this. And there's one more avenue: catching an accretion-induced collapse in the act. If a white dwarf somewhere in the nearby universe crosses the Chandra-Xikkar limit and collapses into a neutron star, the event should produce a faint, fast optical transient, detectable by the wide-field survey telescopes that are now scanning the sky every few nights. The Vera Rubin Observatory in Chile, expected to begin full operation soon, will photograph the entire visible southern sky every few nights with a camera sensitive enough to detect objects 10 million times fainter than what the naked eye can see. Its automated software will flag anything that appears, brightens, or fades between images. A faint, fast transient consistent with an accretion-induced collapse would be exactly the kind of event this system is designed to catch. It might also produce a brief pulse of neutrinos detectable by neutrino observatories, and possibly a weak gravitational wave signal at the very edge of current detector sensitivity. Identifying even one such event would confirm that accretion-induced collapse happens. If the resulting compact object subsequently shows magnetar-like activity, the connection between this formation channel and the magnetar population would be established directly. The truth is that we stand at a point where the question is open and the tools to answer it are either already available or close to becoming so. The next decade of observations will almost certainly clarify whether SGR 0501 plus 4516 is a mundane case with an unfortunately faded remnant, or the first confirmed example of a magnetar formed outside the conventional pathway. Either answer would be scientifically valuable. One would reinforce and refine the standard model. The other would expand it in ways that reshape our understanding of how the universe produces its most extreme objects. And this brings us to the deeper lesson embedded in this entire story. It's a lesson not just about magnetars or neutron stars or supernova remnants, but about how science actually works when it's working well. For decades, the origin of magnetars seemed settled. Massive star dies, core collapses, neutron star forms with an extreme magnetic field, supernova remnant marks the birthplace. Every known magnetar fit this picture. The theory was elegant, consistent, and supported by observation. There was no pressing reason to question it. Then one object refused to cooperate. One magnetar's motion didn't point back to the expected remnant. One set of measurements didn't match the prediction. And that single discrepancy, far from being an embarrassment or a failure, became one of the most productive leads in the field. It forced astronomers to revisit assumptions they had stopped questioning. It drew attention to formation channels that had been theorized, but largely ignored, because the observational motivation to take them seriously wasn't strong enough. It connected the study of magnetars to fast radio bursts, to gravitational-wave astronomy, to the chemical evolution of galaxies, creating links between subfields that had previously operated largely in parallel. This is what a good anomaly does. It doesn't just say, something is wrong, it says, something is interesting here, and if you follow it carefully, you might learn something you didn't know you needed to learn. The history of astronomy is built on anomalies like this. The anomalous precession of Mercury's orbit, which didn't fit Newtonian gravity, led Einstein to develop general relativity. The anomalous rotation curves of galaxies, which didn't match the expected distribution of visible matter, led to the discovery of dark matter. The anomalous dimming of distant Type 1a supernovae, which didn't match a decelerating universe, led to the discovery that the universe's expansion is accelerating, driven by the mysterious force we now call dark energy. In each case, one stubborn data point that refused to fit the accepted picture turned out to be a signpost pointing toward a deeper truth. SGR 0501 plus 4516 may or may not be that kind of signpost. It might turn out to have a perfectly ordinary explanation, a faded remnant, an inaccurate age estimate, a coincidence of geometry and timing. The title of tonight's story says, "May for a reason." Nothing is proven, nothing is settled, the science is still unfolding. But the possibility that this magnetar represents something genuinely new, a formation channel that doesn't require a massive star to die in a conventional supernova, is tantalizing precisely because of what it would mean for so many other areas of astrophysics. It would mean the universe has more ways to build extreme objects than we realized. It would mean magnetars can appear in environments and at times we didn't predict. It would mean some fast radio bursts might originate from objects whose very existence challenges a decades-old paradigm. And it would remind us once again that the universe is under no obligation to match our expectations. Tonight, we followed a magnetar's path backward through time and found that it led somewhere unexpected. Not to the supernova remnant that everyone assumed was its birthplace. Not to any obvious explosion at all. We explored what that absence might mean, from the mundane to the extraordinary. We considered faded remnants and unreliable age estimates. We considered neutron stars spiraling together and colliding in bursts of gravitational waves. We considered white dwarfs quietly accumulating mass until they crossed a threshold and collapsed. Each possibility tells a different story about how the universe creates the most intensely magnetized objects in existence. The case is not closed. It may not be closed for years or even decades, but that's not a weakness. That's the strength of science, the willingness to sit with uncertainty, to hold multiple hypotheses in mind simultaneously, to let the evidence accumulate until the answer emerges on its own terms rather than on ours. SGR 0501 plus 4516 is out there right now, drifting through the galaxy at hundreds of kilometers per second, occasionally releasing bursts of X-rays and gamma rays from its impossibly magnetized surface. It doesn't know it's a mystery. It doesn't know the teams of astronomers on a small planet, thousands of light years away, are arguing about where it came from. It's just a neutron star, 20 kilometers across, carrying a magnetic field strong enough to rearrange atoms, born in an event that may have been quieter and stranger than anyone originally supposed. And somewhere in the data we haven't yet collected, in the observations we haven't yet made, in the instruments we haven't yet built? The answer is waiting. All we have to do is keep looking.